Welcome to The Explainer. Today, we're breaking down a topic that is universally relevant, but honestly, kind of completely misunderstood. You know how fats are always labeled as these huge dietary villains? Well, they're actually our body's most concentrated source of energy. Today, we're going to totally demystify fats, visualize their molecular mechanics, and show you exactly how to translate this invisible science into visible exam success.
So it's the ultimate question, right? Are all fats just dietary villains? To figure that out, we have to look past the food on our plate and zoom way down to the microscopic level. Because here's a pretty fascinating twist. Some fats are actually kinkier than others. And that tiny, invisible structural kink fundamentally changes not just their physical state, but their entire impact on our human biology and health.
Okay, let's dive into this. Here's our roadmap for today. 1. The truth about fats. 2. The chemistry of fat. 3. Saturated versus unsaturated. 4. Fats in our bodies. And finally, 5. Acing the exam.
All right, kicking things off with Section 1, the truth about fats. Are they just villains?
Fats, or as they're scientifically known, lipids, are literally the body's most concentrated source of energy. Getting this baseline fact is absolutely crucial. Not only is it foundational for racking up marks on your biology exams when you're tested on nutrients, but understanding the sheer energy density matters immensely for making informed, healthy dietary choices in real life.
Moving right along to Section 2, the chemistry of fat. Let's see how we actually construct a molecule.
Take a look at these three vital variables: carbon, hydrogen, and oxygen. These are the fundamental building blocks of all lipids. Every single fat molecule, without exception, begins with exactly these three elemental ingredients.
Now, let's build it step by step. In step 1, glycerol bonds with the fatty acids. Then, in step 2, a condensation reaction kicks in. And in step 3, watch how this separates right here. Water is actively released. That release of water is exactly why fats are hydrophobic, which just means they're water repelling. If you can visualize that water molecule breaking away, you are always going to remember why oil and water just do not mix.
Section 3. Saturated versus unsaturated. A tale of two fats.
Okay, so saturated fats are defined as fats with zero double bonds between their carbon atoms. Notice how the structure is completely 100% saturated with hydrogen atoms. Because there are no double bonds, they form these perfectly straight carbon chains. Try to visualize strong, inward directional arrows pulling those straight chains tightly together, packing them so densely that they literally become solid at room temperature, just like a stick of butter.
Now on the flip side, we have unsaturated fats. These are fats containing one or more double bonds. See that double bond highlighted right there? It actually introduces a physical kink into the chain. And because of these microscopic structural kinks, the molecules physically cannot pack tightly together. There's just way too much space between them, which leaves them in a liquid state at room temperature, kind of like the olive oil sitting in your kitchen.
Let's lock this in by looking at the micro and macro together. Over here, we've got our saturated fats from animal sources. The microscopic straight chains align perfectly to create that macro solid block of butter. And over there, are unsaturated fats from plant sources. Those microscopic kink chains create really loose boundaries, resulting in the macro liquid state of olive oil. By connecting that invisible atomic structure to the visible physical state, you have just mastered one of the most critical concepts in biology.
Up next, Section 4. Fats in our bodies. What are their essential roles?
You know, there's a major misconception out there that all solid fats are automatically terrible, and, well, all fats are just bad. That's completely untrue. Our bodies heavily rely on fats for three essential functions: massive energy storage, vital thermal insulation, and acting as a physical shock absorber to protect our vital organs. Fats are absolutely essential for us, provided we manage the type and, of course, practice a little moderation.
And finally, Section 5, acing the exam and securing those maximum marks.
If you're sitting for an O-level biology exam, you are incredibly likely to see a prompt exactly like this. Complete the table to show the differences between saturated and unsaturated fats. So let's build out the perfect response right now. Consider this your ultimate cheat sheet. Check out how the columns systematically break down the data. First row, saturated fats. The state is solid, the structure is straight chains, and the source is typically animals. Second row, unsaturated fats. The state is liquid, the structure is kinked chains, and the source is typically plants. If you can just visualize this exact grid on test day,
Mapping that physical state straight to the molecular structure and the biological source, you are going to secure maximum marks every single time.
But if you want to grab those extra distinction marks, you really need to understand the why behind dietary advice. So here's a really high-value follow-up question. Which type of fats is more recommended in our diet and why?
The explicit answer here is unsaturated fats, primarily because they improve heart health by actively reducing bad cholesterol levels. That loose, kinked, structural nature of unsaturated fats, it actually translates into a much more positive biological flow for your cardiovascular system, physically lowering those bad cholesterol numbers. Being able to explain that exact mechanism is what sets the top students apart. So the crucial point is really captured right here in our quick-fire recap flowchart. Let's trace it through one last time. Lipids are glycerol bonded to fatty acids, which releases water in a condensation reaction. Saturated fats equal straight chains packed tightly into solids. Unsaturated fats equal kinks chains flowing loosely as liquids. And lastly, those unsaturated, kinked fats are generally healthier for us because of their ability to lower bad cholesterol.
Which leaves us with one final thought. We've taken this invisible world of microscopic bonds and shown how they dictate literally everything, from the melting point of your food to the health of your heart and even your success on an exam. So next time you're in the kitchen making a choice between butter and olive oil, will you visualize those invisible molecular kinks shaping your health? Thanks so much for watching this explainer, and keep visualizing the science around you.